All right, gang. Right now what I want to do is talk about the projects. As I've mentioned before, the projects are optional. Usually I don't make them optional, but they're going to be optional. If you do the project and you like your grade on it, you can use that grade as your final exam grade and skip taking the final. So if you feel like taking a final and blowing off the project, you could do that. However, if you do the project and you don't complete it, or you do poorly for some reason, you completely don't implement something correctly, or you turn in something that doesn't work, you wouldn't get a good grade on it and you'd want to take the final. So I will have the projects graded by a week before our finals begin, so that you have a chance of knowing whether you're going to take the final or not. Let's go look at the projects. There's 4 ideas for them. I'm going to start from 4 and work my way up. I kind of wish I'd opened a Word document. Can we get rid of that? Yeah, there we go. Monster array. Project 4. Write a program that shows the path of an imaginary monster moving through a 2-dimensional array trying to eat the highest values in the array. As the monster goes, it leaves a trail behind it. Imagine a 40 by 40 array displayed like this. Well, not like this. I need to edit this slightly. Like this, where the zeros have been replaced by dots. Obviously, that's not a 40 by 40 array, but for sample output, it'd be a real drag, printing 40 lines every single time. So this is with an 8 by 8 array. But when you implement it, you could start yours with an 8 by 8 array, but you're going to do a 40 by 40 array. So you're going to declare your array. You're going to place the values 2 through 9 randomly in the array. So 2, 3, 4, 5, 6, 7. Looks like I forgot the 8 and the 9. Whatever. To make our output clear, I want you to print all zeros out as periods and ones as symbols. Well, there are no ones yet, but there will be. The ones represent the trail of the monster. So once your program can produce that output, write code that will simulate the monster. It starts at element 0, 0 right here in the corner, and it moves to the 7 each time, leaving a 1 behind it. Now, the only rule there is that it can't move diagonally. So you have to decide, whether you're going to move it horizontally or vertically. And the algorithm you choose to get it to go to the 7 is up to you. I tried to write one that would, do a kind of a diagonal movement to get there. Once it reaches the 7, as it goes, it replaces every value on its way with a 1. Once it gets to the 7, then it'll look for the next highest, which would be the 6, and then 5, and so on. And if it accidentally overwrites a value on the way to the highest one, that's okay. So here's sample output. Here's our starting array. Then the monster begins moving. Monster on the move. The monster wants a 7. So we put a -1 there in the corner. We're moving towards the 7. I decided to move that way. I decided to move that way. This should all be algorithmic. You don't ask the user whether he's going to move, to the left, right, or up, and down. And now he's moved down 1, but he erased the 4, replaced it with a -1 on the way. He keeps moving towards it. He keeps moving towards it. I hope you can see what he's doing. He's kind of heading diagonally towards it with up and, with down and to the right motions. He's almost there. Then he covers the 7, so we print out the message, monster ate the 7. At that point, the monster has reached the target. Then we look through the array again, finding the coordinates of the now highest value, right? Because these are all 1s. The 7 is gone, so that becomes the highest value. So then we print monster on the move. The monster wants a 6, and it moves there going towards the 6. And it goes towards whatever the highest one is, 5. The 4 already got erased, the 3 and the 2. Once there is nothing in the array except zeros and ones, dots and trails, then the simulation is over. So you can read a more detailed explanation and the requirements for the program in the document. That's the first one, or the fourth one. Selection sort versus bubble sort. As you may know, there are different types of sort algorithms. The selection sort and the bubble sort are easy to implement. There are some that require a lot more work to implement. They are more efficient. These are not terribly efficient, but they're easy to understand, so they make good little projects. So write a program that implements a selection sort and a bubble sort. Compare the number of comparisons and swaps performed by the algorithms to process the same array of 10,000 randomly created integers. So you're going to make an array of 10,000 randomly created integers, or maybe you're going to make, two of them with the same values in it. One's a copy of the other. You're going to run a selection sort on one. You're going to run bubble sort on the other, and as they run, you're going to be keeping track of the number of comparisons and the number of swaps required to do those algorithms. And then you can say, okay, selection sort took 60,000 swaps and 80,000 comparisons. These numbers are totally off. And the bubble sort took 70,000 swaps and 230,000 comparisons, or whatever. So what I do is I give you Python code for doing a selection sort and a bubble sort. I should have made you work on it yourself, but what people tend to do is they just go and they find code and they copy and paste it. And so I would rather you translate this code into Java. Fortunately, Python is so clear, I hope, that you'll be able to know how to write it in Java. I want you to turn this stuff into Java rather than just going out online and copying and pasting, a bubble sort code. I'll be able to tell if you did that because it will look considerably different. Try to maintain my variable names. If you have difficulty understanding the Python, then either you want to pick another project or you want to come and talk to me about it. But it should look like pseudocode. The only thing, hopefully that makes sense. So you can tell in these algorithms, in these Python codes, where the swaps occur, right there, and where the comparisons occur. So you're going to want to keep some counters. Every time you do a comparison, you're going to want to update the counter for the bubble sort comparisons. Every time you do a swap, you're going to want to update a counter for the bubble sort swaps. Same for the other sort algorithms. Selection sort. You can tell where the comparisons happen. Every time you do that comparison, increment a selection sort comparison counter. Every time you actually do the swap, do that. And I implemented swap, or suggest implementing swap, as just a silly little function, silly little method you can call. Alrighty. So the code above doesn't keep track of the swaps and the comparisons, but you will. Alrighty. So that's project 3. Project 2, Caesar Cipher. A lot of people like this one. Write a Caesar Cipher program that will display all possible permutations of an input string, shifting the characters over the ASCII chart from the ASCII values 32 to 126. 32, I believe, is a space, 126 a lowercase z. So anyways, if the user typed in A, B, C, D, E, F, the quick brown fox, the output is going to be shifted character by character. You can Google up what a Caesar cipher is or read this explanation more carefully to understand if you've never encountered it before. All it does is if you shift once, an A becomes a B. If you shift twice, an A becomes a C. If you shift 3 times, an A becomes a D, and so on. So if we were shifting that, we would shift it. That's what it looks like unshifted. And then when everything is shifted up by a value, it goes like that. And then it does some wraparound, right? Because at the upper value, it's got to wrap around all the way back to the lower value. And so some people, when they do a Caesar's algorithm, they just swap Z's. They shift Z's going back to A. But instead, we're going to use ASCII values to shift 126 back down to 32. So in our sample output, it keeps going. You can see that as we shift more and more, it becomes completely incomprehensible. By the time we have shifted everything around, it prints that again. I forget why it prints tildes there. Something about the shifting that I did converts spaces to tildes, and I don't recall why. If yours wraps around and the spaces are maintained as spaces, great. If you implement my algorithm perfectly and the spaces wind up being tildes, that's also fine. So then what I want you to do is I give you an input string that's already been shifted. And if you enter that into a program like this, then it'll do, all possible 95 permutations of it, and you'll be able to spot which one is written in English. And that's your answer. That's what you get. And then I will want you to turn in the program and put a comment in there as to what the string originally was before it was encrypted with Caesar Cipher. I guess encrypt is the wrong term if it's a mere cipher. Cipher is just a replacement algorithm. So here's all the explanation of a Caesar cipher. If you're shifting 3 in classical style, R becomes a U, right? QR, S, T, U, and an E becomes an H, E, F, G, H. Everything's going 3 over. And a Z shifted 3 times would become an A, B, and C. So far. But that didn't encrypt punctuation. So you're going to want to do punctuation. And then there's some explanation. There's even some sample code, which makes it too easy. I should delete the sample code, but I'm going to leave it in there. All right, that's the Caesar cipher. And the last one looks more, well, let's go take a look at it. This makes it look really cool, this diagram here, but this diagram is an explanation. Write a program that will accept a series of numbers representing bytes generated by a keypad, then processing that result as a calculator would. Now, as I recall, I don't ask you to write the keypad. I just ask you to enter the series of digits that the keypad would generate. So the problem really is broken into 2 things, and I only ask you to solve the second half of it. If you wanted to do the first half of it and to write a GUI, a graphical user interface, which would let you press buttons on here and generate a string of output, which you could then copy and paste as input into the other part of the program, that'd be cool, but I'd give you extra credit for it, but that's not the requirement. So the explanation is that if you pressed 7 on this calculator, remembering our binary values, it would light up that one and that one. You see that there's this kind of grid of wires. Whereas if you press divided by, it would light up that one and that one. And then you could translate those into binary numbers. So if you typed in these binary values, that these things were going to result, except not as binary, but as values between 0 and 255. Please enter a series of integers. -1 will stop the input. So if they type in a 136, that's a 7. If they type in an 18, that's a plus sign. If they type in a 132, that's a 4. If they type in a 132, that's a 4. An 11 is a that, and a 15 is a that. And last time I had these instructions out, somebody told me that I had some of these wrong. I will go back and verify them. So, explanation. If you press a 7, it lights up that bit and that bit, which is 100100, which converted to base 10 is 136. Then if you hit the plus sign, that activates bits 4 and 7, which is 0010010, which is 18. So that means that this explanation up here where I said that, yeah, okay, I did get 18 there. And so on. When they press 4, it lights up that line and that line, so it becomes 1000100, which becomes 132, and so on. If more than 2 bits are active, it's invalid input and should be completely ignored. So if somebody enters a value in here that doesn't correspond to anything that this could generate, you just ignore it. So they enter a series of values, you turn them into some good values, 7 plus 44 equals, and you evaluate that as 51. So you can read these instructions for more understanding if that's the one that you're interested in. So just pick one, work on it. I really hope that y'all do one. I think it'd be a lot cooler than taking the final myself. A lot more interesting. Some of these may be a little bit easier than others. Just pick the one that interests you, or pick which one you think is going to be the easiest, you know, whatever criteria you're going to choose. But just try to make it a learning experience. All right, I hope that makes sense. I'm going to stop the recording here, and then we're going to start again for the lecture.